All right, now, hopefully you have watched the friction force demonstration video, which is still behind me for the last task that I did. And now what I'll do is go through some of the notes to try to explain what happened a little bit better. Okay, so let me change my camera. Notes, and I'll try to get set up so I'm not gonna make a mess here. So I probably will. All right, too much paper. Okay, so let's talk about what happened, and what we're dealing with is friction force. And what I am going to tell you is this is just a special name for force. Sometimes we have names for forces to be able to refer to them quicker and more specifically. And but it's also easy to get things a little confused because sometimes there's a little bit of duplication. All right, so friction is the force that occurs between two objects sliding over each other. Okay, the force that occurs due to two objects sliding over each other. What I did the first time in that video is I took that weight, and I hope you don't mind, I'm just going to draw the weight as a box. Okay, that's the weight that I had. And this is the force platform. And I'll just do, I don't want to, force platform. And the force platform that I'm using here measures force in 2 dimensions. Remember, ground reaction force is 3 dimensions. So what a force platform does is measure the ground reaction force. And the ground reaction force is 3 dimensions. We can call them X, Y, and Z, or sometimes we will say medial lateral, depending on if we're in the lab, or anterior posterior, or vertical. Now, depending on which lab you're in, or depending on which lab, maybe country, you may use a different symbol for each of these descriptors. Some labs call anterior posterior Z, some call them X, whichever way it is. The most important thing is that we define what the letters represent with the word descriptors. All right, and if I drew this, I would draw the ground reaction force as a 3-dimensional arrow in a reference frame. And I would do Y, X, and Z, the way I've done this here. And then I would draw the different components of this force. I'm not very good at 3-dimensional drawing, but that would be the Y component of the ground reaction force. This would be the Z component. And then coming the way I've drawn this here, this would be the X component, thinking that this is maybe coming out, pointing out of the paper. Okay. So each of those are independent of each other. They're orthogonal to each other. They're at 90 degrees to each other. This force platform can measure each dimension by itself. And really, it only measures 2 dimensions at one time. And that's the vertical and the anterior posterior, or one horizontal force. We could set that sensitive axis in either direction, but that's what we're going to do. We're going to call it the anterior posterior force. Okay, so, but the ground reaction force is a 3-dimension force. Good to know. Good to know. We need to know that. And sometimes we focus in on one dimension or another. All right, so this was the first task that we did. Let me I'm going to keep that page nice and clean for notes. Let me do it again here. Draw that same. I'll scan these notes and I'll post them for you. Here's the force platform again. Here's the ground, and this is our weight. So what did I do? I came in and I pushed on the weight. It's me pushing on the weight. The weight did not move, okay? The weight did not move. So knowing when we do our kinetic analysis, we identify all the forces acting on the object, and then we put those forces in this equation. And what's really important is we're going to do one dimension at a time. So I'm only going to, right now, deal with horizontal, or oh my goodness, horizontal, I spelled that terribly. Horizontal direction. I'm not going to concern myself with the vertical or if there's any side-to-side movement, okay? So I can put horizontal as a subscript here, and I can do horizontal as a subscript here, just to remind myself that I'm only going to concern myself with horizontal movement. All right, so what other forces are acting on the object? Well, and there's a couple ways we can go. We can think about it, or we can look at the equation as well. The forces acting on the object have to add up to the product of mass times acceleration. Mass is a fixed quantity. That weight is not changing its mass. Acceleration is rate of change of velocity. Remember, acceleration as 0, a equals delta v over delta t. If velocity is not changing, acceleration will be 0. Velocity is not changing, and in this case, velocity is 0 meters per second at any moment in time, meaning acceleration will be constant. 0 acceleration does not mean 0 velocity. 0 acceleration means constant velocity. 10 meters per second, 10 meters per second, 10 meters per second. That will result in a 0 acceleration, constant velocity. In this case, constant velocity is 0. So if this force is acting on the object, there must be another force. And that force has to be the same magnitude and in the opposite direction so that they add up to 0. That is not Newton's third law of motion, by the way, okay? That is not Newton's third law of motion. These are forces acting on the object. I'll draw it over here just because it may make more an intuitive sense if I put it here. This is the ground reaction force in the horizontal direction. Yeah. Okay. I drew that as the same length as that and in the opposite direction as that. That is not Newton's third law. Now I better write that here. Not Newton's third law. So many people get that wrong. That is not Newton's third law. What Newton's third law says is for every force acting on the object, there's an equal and opposite force created by the object. That means the weight is pushing on my hand. The ground is pushing on the weight is pushing on the ground, okay? Forces come in pairs. These are forces acting on, really important, on the object, okay? So it's not Newton's third law, not Newton's third law, okay? I'm pushing on the object's pushing back on me. The ground is, the weight is pushing on the ground is pushing on the weight, okay? Obviously these are all linked, but we need to get them straight. All right, so now if I add in the force of my push plus the force of the ground reaction force in the horizontal direction, that has to equal 0 in the horizontal direction. I'm using H first, subscript. These have to add up to 0. This is a negative force. I should have reference frame. Up is positive, oops, up is positive, and forward is positive. So if this is positive here, this is a negative force pointing in the opposite direction is positive. Whatever force I push with, this ground reaction force ends up equaling that, and we're going to get zero force. That is not Newton's third law, okay? It is not. All right, because at some point, these two forces will not be equal to each other. And then what are we going to do? Say Newton's wrong? No. So we're good to that. For every force acting on the object, I'm put on here and on here, okay? There's an equal and opposite force created by the object that we're not putting into this equation, okay? Just acting on the object. All right, so if I push with 10 newtons, the ground reaction force is 10 newtons. Not Newton's third law, okay? If I push with 50 newtons, it's going to be negative 50 newtons. And we saw that on the screen. We saw that. As I pushed, the ground reaction force varied in force as well. But it's not Newton's third law. Okay, let me number these. All right, this is number 1. I'm going to be too wordy here. This is going to be too long of a video. You're all going to turn it off. All right, so that's what I did first. And when if I draw a little scope up here, okay, and I'll do it this way. Here's force here, positive, negative, and this is time on this axis. Always label your axes. And this is the ground reaction force. So as I pushed on the object, the ground reaction force fluctuated with my pushing of the object. Okay, that's what we saw, something like that, whatever it was. And it's negative because the ground reaction force is pushing back in that direction. I guess I could have completed the description. I could have pushed that way, and then the ground reaction force would push that way. Not Newton's third law. All right, let's look and see why it's not Newton's third law. All right, let's do the ramp. So what I'm going to do is draw a ramp, and I'm going to draw, well, let me do a small ramp first, and then I'll do a steeper ramp and try to show you that part. I've got another video on this later on, so you'll see this again because we're talking about cycling uphill and downhill. What forces are acting on this object? The ground is pushing up on the object, okay? The ground reaction force is pushing on the object. The ground reaction force is 3 dimensions. And in this case, we would call the 3 dimensions normal to the surface, okay, and parallel to the surface. Normal meaning at 90 degrees. Okay, that's what we're gonna have to shift. So this would be level, and this is going downhill. All right, so the ground reaction forces act down here. I'm not going to draw that right now, okay? I'm just going to draw the other force. Okay, just draw gravity. And I'm going to draw that rather large so we can see what's going on here. This is the force due to gravity. Gravity is a force pulling on all objects. And it's pulling vertically relative to the true surface of the level of the surface, okay? But this object is on this ramp. So what we need to do is decompose this force vector into 2, and if we're doing 3 dimensions, 3, but we're going to decompose it into 2 force components. One that's parallel to the surface, and one that's perpendicular or normal to the surface. Okay, we're going to do this every time, and we'll stick with 2 dimensions. But we could do 3 dimensions, and ultimately, if we do movements in the real world, we have to deal with 3 dimensions as well. All right, so again, I've got a video on this later on, but I'll show you now what you do to identify those 2 components of the force vector due to gravity is I'm going to draw a rectangle around this arrow. And I'm going to draw the rectangle so that two corners of the rectangle are at the origin and at the tip of the force vector. So this is going to be one corner, and this is going to be a kitty corner, the opposite corner. So I'm going to draw a rectangle. Now, it takes it sometimes your brain a little bit to get used to doing this. Well, we're going to draw a rectangle. My brain didn't work too well, but that's a rectangle. Okay, 90 degrees, 90 degrees, 90 degrees, 90 degrees. Once you have that rectangle, and you got a kitty corner here, okay, this corner and this corner. Once you have that drawn, then you can identify the component or the side of the rectangle that's parallel to this surface, and the other one that's normal or perpendicular at 90 degrees to the surface. This is going to be F, and sometimes we just write two parallel lines like that. This we would write, we'd either say F sub n or F perpendicular. You'll see a lot of textbooks also call this, so they'll use subscript n for normal. But now I've got these two force components, and now I can do my kinetic analysis in the dimension I'm interested in, which is the dimension parallel to the surface. So now I can still say horizontal, but I really mean parallel to the surface. Okay, so now I'm going to identify in my kinetic analysis the forces acting on the object. Okay, we've got these forces, but I only want to do horizontal, so I'm only going to concern myself with the parallel component. Yes, I should have. Okay, we're going to identify the forces acting on the object, put it into this equation. Parallel force, this is the force component due to gravity. What other forces acting on the object? Okay, I just drew gravity, but now the other force is GRF. Ground reaction force. Now, the ground reaction force is also acting in the normal direction, and it's also acting in the parallel direction. Okay, that parallel force is right here, pushing against the object. I'm going to draw them to be the same length. So now this is ground reaction force. On my force platform, this is still Y, because I tilted the force platform upwards. These two are supposed to be the same length, okay? This one and that one. So F, GRF, Y. On my force platform, this is positive and this is negative. Now we're going to take those two forces and put them into this equation, Newton's second law. And that's what we get. Now, as long as the object is not sliding, the acceleration is zero, because V is 0 meters per second. As long as the object's not sliding, V will stay 0 meters per second, meaning acceleration will be 0, meaning these two forces are going to be equal in magnitude in their opposite direction. Not Newton's third law. We're not there yet, okay? Not Newton's third law. These are forces acting on the object, not by the object. Newton's third law, for every force acting on the object, equal and opposite force created by the object. I can't tell you how many people do this wrong, where they say this is Newton's third law. It's not Newton's third law. Yes, this is equal in magnitude and opposite direction to that. That's not Newton's third law. That just is the situation that we have. All right, so the object's not sliding. Now, oh man, where are we? 3? Okay. Now let's see what happens when let's do this again for when the object did slide off. writing on my clean piece here. So now I'm going to make this steeper. Okay. I'll make it really steep just so we can see it. I'm going to try to draw everything about the same size, okay? So here's my object. Okay, I'm going to draw gravity from the center of mass of the object, F sub G, I'll label it. Now I'm going to break the force of gravity into two components, the perpendicular, the normal, and the parallel. Kitty corner, draw a rectangle. Let's see what I do here. Okay, that my side of my rectangle showed up right there. There's my rectangle, kitty corner. One corner, 90 degrees, 90 degrees, 90 degrees, 90 degrees. Now we can identify the parallel and the perpendicular or the normal force. And I keep my origins lined up. Okay, that side is the perpendicular force, the normal force. And this side of the rectangle is the parallel force. Okay, let's do the same thing. Let's do our kinetic analysis, but we're dealing with horizontal, really parallel. Okay, we're dealing with movement along this surface. Kinetic analysis, identify the forces acting on the object. We have the force due to gravity, but now I'm only going to put, because I'm only interested in this dimension, F parallel, the component of the force vector of gravity acting on the object. Okay. And what other forces acting on the object? Gravity action force. And I'm only going to do this one right here. F, G, R, F, Y. Okay. Now, this is, let's say this is right after the moment the object starts to slide. So initially, VI is 0 meters per second. But at some moment, right before or right after the object starts, right in that instant of time, the next velocity is going to be something positive, because positive is going downhill here. That's an equal sign. It's going to be positive. Let's just put a number on. Let's say 1 meter per second. Sorry, I guess I did 0.1 meter per second. It doesn't matter. That's fine. Okay. 0.1 meter per second. It's positive. It's positive. Okay. So now what other force? F, G, R, F, Y, negative. Why? Because it's pushing in the opposite direction as our reference frame. So what do we do now? We put these forces into this equation. And we're dealing with horizontal movement, and we have F parallel plus F, G, R, F, Y equals MA. Let's see what's going on now. Is acceleration going to be 0? The answer is no, because I have a change in velocity. Remember, A is delta V over delta T, final minus initial velocity. So that's going to be some number. If I put a delta T on here, then I'm going to get I can actually calculate my acceleration. I can give you a mass. I can give you, we're going to get something on the right-hand side of the equation that's not 0. That means these two forces are no longer equal in magnitude. That's why I was saying it's not Newton's third law. All right. Before, every time I said it, I said here, equal magnitude, opposite direction, not Newton's third law. In this case, because the object is accelerating, because the object is changing velocity, this pulling force due to gravity is exceeding this force right here that's pushing back on the object. I should have used a different marker color. Sorry. Okay. That force is greater than that force. That's not Newton's third law. Well, it never was, okay? Newton's third law always says for every force acting on the object, there's an equal and opposite force created by the object. Now, these two forces are not equal in magnitude, and I have an acceleration. So the force that we see right before the object starts to slide is the maximum static friction force. Right? Maximum static friction force. Once we exceed that, the object starts to slide because that stickiness of the surface starts to reduce the amount of friction force that can be pushed back on the object. So when I put the piece of wood on there, and I won't draw that out now, the wood, I'll do it extreme. This is number 2. This is number 1. This is with the wood. The object started sliding sooner. Why? Because there was less friction force. Excuse me. Yeah, there was less friction force acting on the object. And if I did my parallel component of the force due to gravity, it would be smaller here, meaning the maximum static friction would be less. Oh, okay. Open page 4 here. All right. So let me go back to my other camera then. And I lost that computer. Oh, let's see, it's down here. Wrong password. Let's try again. Okay, so that was the object on the wood, and it started sliding sooner at less force. So as I lifted it up here, I'll just hold it for now. It started to slide. There it goes. At that point, the parallel component of the force vector due to gravity is less than the the parallel force. It's late for me too. The friction force is less than the parallel component of the force acting on due to gravity. The parallel component of force acting on the object due to gravity is pulling on this object. And eventually it's going to win that tug of war. Friction force is pushing against it, and there it goes. Once that object starts sliding, the force due to gravity in the parallel component is greater than the friction force. That's why that's not Newton's third law. Okay. Now, I have the object here. The friction force was greater because the friction force is a function of how the two surfaces interact. By putting a smoother surface on there, I'm reducing the ability for friction to occur, and the object's going to slide sooner. That's why you slip on ice, or what, if the floor is super polished, you put your foot down, and the maximum static friction that you can have between your foot and the surface, the slippery surface, is really small, and so your foot comes out from underneath you. But by having more, this is like sandpaper on here, that's going to make it super sticky. All right, friction force is pretty. But there it goes finally. Go sooner. Hopefully. start sliding sooner. The component in the parallel direction due to the force of gravity is less here. The friction force is less as well. All right, that's fun. Hope you enjoyed it. And I'll check in and see if you have questions on that. I can do a follow-up video again, and we can put some numbers on it too if we need to. All right, thanks everybody.